Hey everyone, I'm gonna be going over a quick question or a three-part question on degrees and sort of undirected and directed graphs. So let's get into it. We're given some definitions. In an undirected graph, the degree of a vertex U is the number of neighbors U has, or equivalently the number of edges incident upon it. So if we have vertex U and some random vertices it is connected to, the degree of U is 3, and all of these have degree 1. In a directed graph, we have there's a distinction between an in degree, sort of what points in, and an out degree, then the number of edges that leave U. So here it has an in degree of both 1, an in and out degree of 1. So let's get into the question. First up, we have to show that in an undirected graph, the sum of all degrees of all the vertices is equal to 2 times the number of edges. So let's see. First, I like to draw out a graph to sort of visualize what is happening. What we're doing here is we're counting up the degrees of all of these vertices. So here the sum is going to equal to 4. And we'll see that it is equal to the twice number of edges. So let's see how we can rigorously prove that claim. First, let's write down sum of all the degrees. Then I guess we can expand the degree like sort of function out into another sum. If we sum over all the vertices and sum over all the edges, we can now just add 1 to the sort of counter, and this is going to, since this is a undirected graph, this is going to sort of count over every vertice and add up and add 1 for every edge that sort of that vertice contains. And you might sort of think, well, it double counts the edges since first we're gonna have this BU, and we're gonna add 1 here, and then we're gonna have this BU, and we're gonna add another 1. Well, that's sort of where we're gonna have. That's sort of where the 2 is gonna come in. Now, if we don't want to double count, we can just say that every edge contributes 2 to the sum. So we're gonna get rid of one of these sums and just say that every edge in the graph contributes 2 because like I already said, is going to contribute for every edge V is going to contribute 1 degree to U and 1 degree to V. And since this is summing a constant over a space of size E, we can just say that it's 2 times size of E, which is the number of edges. Hopefully that makes sense. It's sort of you can see it very intuitively that every edge adds 1 to the degree of both of its vertices, which means that the total sum of degrees is going to be 2 times the number of edges. For part B, we'd like to show that in an undirected graph, there must be an even number of vertices whose degree is odd. So what we can do is we can sort of think about splitting up the graph into the vertices with an odd degree and the vertices with an even degree. Now, sort of our equation from part A is going to look like summing over the odd degrees and summing over the even degrees to get 2 times the number of edges. So we're going to add up these two sums and get an even number in the end. So let's rewrite this. And we can, since for this sum, we're adding up even numbers. No matter how many sort of even numbers you add up, you're always going to end up with an even number. And we can call it, say, 2a. where let sort of 2a be that sum, and we know that it's going to be even. Now, since we have now in this equation, we're gonna have an even number summed with some unknown, which is going to result in an even number. Now, from CS70, you might sort of figure out that this number also has to be even. Let's call it 2b, and it actually has to be equal to it is going to be equal to this sum. So let's sort of rewrite this. And say it's equal to 2b. Now, we're in this sum, we're summing up odd numbers, and in the end, we're getting an even number. And once again, from CS70, you if you rewrite each of the degrees as some as like 2u prime, or let's call it sort of 2c of u, where c of u is sort of the degree. We'll see that the degree is going to equal to some odd number, and then adding up. Since we're adding up a bunch of these odd numbers into an even number, we actually we can say that the size of the odd has to be even. And I'm not gonna prove it super rigorously with CS70 like in a CS70 like proof, but you can sort of convince yourself that that is the case for this part. And last part, we have C. Does a similar statement hold for the number of vertices with an odd in-degree in a directed graph? So now, instead of having undirected graphs, we actually have we can have directed graphs. So A, B, A pointing to B. Now let's sort of see. The in-degree of B is going to be 1, and the in-degree of A is going to be 0. And sort of the number of vertices here with an odd in-degree is only going to be 1. So we can already see that that the same cannot be said for directed graphs. And you might sort of think, well, why is that the case? Well, and sort of an undirected graph can be represented as a directed graph with sort of 2 edges for each edge in the undirected graph. And this means that sort of directed graphs are a more generic version of they sort of generalize undirected graphs. And actually, because in undirected graphs you have sort of these 2 edges for every edge in a directed graph, you will have this property of the size of the vertices, with odd degrees being even though you might even though, as you see, like, you're not gonna observe that in directed graphs. I hope that was helpful. Have a great rest of your day.